about prime factorization. Prime factorization has the word factor in it, so you should be knowing your factors. Factors are what numbers make up a multiplication problem. For example, what are factors of 15? 1, 15, 3, and 5, because 1 times 15, 3 times 5. Also, from it, we will be making factor trees. So before we do that, let's review what we learned in previous lesson. I do now. Yes, Yellowstone National Park is known for its 10 to the 4th power hot springs and geyser, which is more than anywhere else in the world. Write 10 to the 4th power as a product of the same factor. How many hot springs and geysers are in Yellowstone National Park? So we have 10 as the base. You're going to write the base. 4 is the exponent. Tell you how many times you're going to use this in this multiplication problem. You're going to use it, you're going to write it as 4 groups of 4 tens. You'll write the number 10 4 different times. So let's multiply this. What's 10 times 10? 100. What's the other 10 times 10? 100. So what is 100 times 100? Well, we know it's 1. How many zeros do you see here? 4 zeros. It's 10,000. Another way you could have done it is 1 times 1 times 1 times 1 is 1. How many zeros do you see here? 4 zeros. 10,000. There are about 10,000 geysers and hot springs in Yellowstone National Park. So, before we know how to do prime factorization and stuff, do you remember your prime, composite, and neither numbers? What are prime numbers? So prime numbers can be like 5. 5 is a prime number. 13 is a prime number. 2 is a prime number. What makes these prime? You remember this from 5th grade, elementary school. Prime number is just 1 times itself. 5 is only composed of 5 times 1. 13 is only 13 and itself times 1. 2 is 2 times 1. Did you know 2 is the only even prime number in the world, in the number system? So, which one are composite? 8, 9, 21, 24, 27, 6, 12, and 51. Why are these composite numbers? Because they have more than 2 factors. For example, 8 is composed of 1 and 8, 2 and 4. Those make up 8. A lot of people look at 51 and say, that's not a composite, that's a prime number, mister. It is. It's 3 times 17 and 1 times 51. It is divisible by 3. So it is a composite number. So which one of these is not? 1 is neither. Because it's only made up of 1 times 1, 1 itself, 1. So it only has 1 factor. While these have multiple factors, and these have 2 factors. So, from these, it's very important when you do prime factorization that you know which one are prime numbers. So, looking at the next screen, name the first 5 prime numbers. Well, 2 is the first prime number, 2 times 1. 3 is the next one, 3 times 1. 5 is the next one, 5 times 1. 7 is the next one, 7 times 1. Skip 9, 11, 11 times 1. When you make prime factorization or factor trees, these are the prime numbers that you're probably most likely going to use. So that's why I always tell kids to memorize them. 2, 3, 5, 7, 11. So prime factorization is finding which prime number multiplied together to make the original number. To find a prime factorization, it is helpful to make a factor tree. So we're going to be making factor tree. You may have made this in elementary school. But however, you probably broke it down into different factors, but you did not build it up with exponents. So let's break this down. So we draw 2 little branches. What are the 2 factors of 135? Well, 135 ends with a 5. So I know it's divisible by 5. I have no idea what the other one is. Let's see. 5 times 27. This is a prime number, so I circle it. So I know I need to stop right there. That's a prime number. 27. Is 27 a prime number? No. It can be broken down into 9 and 3. Which one of these is a prime number? 3. 3 times 1. Again, what are the first 5 prime numbers? 2, 3, 5, 7, and 11. So I know I need to circle these. 9 is made up of 3 and 3. So what prime numbers make up 135? 3 times 3 times 3 times 5. That is a very good answer. I like that answer. In 5th grade, that would have sufficed or been suitable. However, in middle school, I need you to write it with exponents. I do not want to repeat this over and over. I'm lazy. There must be another way to generate this and as an equivalent expression. What about 3 cubed times 5? Or 3 to the power of 3 times 5. Why? Because 3 is written, multiply how many times? 3 times. That's why I write 3 to the power of 3. Again, 3 to the power of 3 is called cubed. So either one is correct. They both mean the exact same thing. So in our last lesson about exponents, you can break this down into 3, 3, 3, and 5. And you multiply it back, you get 135. So try the next example. Ooh, negative 120. When people see that, say, ooh, we didn't work with that in elementary school. I know you didn't. So what two factors make up negative 120? Well, negative 1 times 120. So we know that one. So we'll stop right there. All right, next one. What two factors make 120? 2 times 60. Circle that. What two factors make 60? I could do 6 times 10. 3 times 20. You know what? I'm going to do 2 times 30. I circle 2 because it's prime. What makes 30? 3 times 10. Circle 3. You could have used 2 times 15, 5 times 6. And what makes 10? 2 times 5. This is made of many, many prime factors. I see a negative 1, a 2, a 2, a 2, a 3, and a 5. Is there another way to generate this as an equivalent expression? There's way too many numbers here. What about just negative 1 by itself? How many 2's do you see? I see 2 is written to the power of 3. I see a 3 and a 5. And this is the answer. So instead of writing negative 1 times 2 times 2 times 2 times 3 times 5, we got written negative 1 times 2 cubed times 3 times 5. Next one. Number 6. Let's do a word problem. With 254 counties, Texas has the most of any state in the United States. Oh, has the most of any state in the United States. Generate, to be a period, actually it's kind of a period. Generate an equivalent expression using prime factorization for the number 254. So I need to generate this and break it down. Well, it's even number. So I know all even numbers can be divided by 2. So I do not know it, so I'm going to have to break it down by 2. So it's 2 times 127. How do you break down 127? Or is it possible? Divide by 3? No. I don't think it's possible. It is a prime number. So 2 times 127 is another expression for 254. All right, next one. Let's make something a little more tougher. Oh, goodness. Skip this one. Skip this one. I like this one. The prime factorization of the number negative 144 is going to look like this form. Can you add up those two exponents? So first of all, let's break it down. So we know is negative 1 times 144. What two numbers make 144? 12 times 12. Can you break down the 12s? Yes, you can. 2 times 6, 2 times 6. Which of these are prime? The 2 is a prime. What makes 6? Break down the 6 into two factors, 2 and 3. The 2's are prime. Is 3 a prime? Yes, it is. So, what numbers make up negative 144? Negative 1 times 2 times 2 times 2 times 2 times 3 times 3. That's a great way to write it, but is there another way to write this as an equivalent expression using exponents? Negative 1 times 2 to the power of 4 times 3 squared, or to the power of 2. A is written in this form. They are the same. So A is 4, B is 2. They would like us to add those two exponents together. If you add the 4 and the 2, the two exponents, or two powers, it will add up to 6 is the answer. So let's try a couple more in case you still are having a little more difficulty. So what happens if they give you exponent like this one? Can you generate another expression of this? Can you find a number of it? So 5 squared is 5. You write the base 5 twice. you write the base 3 twice. So what is 5 times 5? 25. What is 3 times 3? 9. What's 9 groups of 25? Let's see. 4 groups of 25 is 100. Another 4 is 100. That's 200. 225 is it. So let's try our last example of prime factorization. 2 cubed times 7 squared. Can you generate a value for this? So you have 2 is the base, you write it 3 times. 7 is the base, you write it twice. So I know 7 and 7 is 49. 2 times 2 is 4. 4 times 2 is 8. So what is 8 groups of 49? 8 groups of 49, 32 plus 7 is 30. 392 is the answer. So what we did in this one is we generate different ways to write an expression. We used prime factorization. We made factor trees. We found the factors, and then we used exponents as another way to rewrite it, as another equivalent expression. Or we are given factors or exponents, and we broke it down and multiply it out, and we got a value for it. So it is prime factorization.